All right, hello again. It's good to see everybody, and it's good to be back at Beaver Summer Institute. How are things going? All right, does everybody know what a node is? Yeah. Ross, no? Good. Ross topic and Ross messages. Everybody know how to create them and send messages across? All right, awesome. Good. I'm glad it's been going well. So today we'll be talking about localization. So I know we started a couple weeks ago talking about all the different pieces, components that go into building an autonomous mobile robot. And we named a lot of different things like motors and sensors and the software that's needed to tie everything together. And we came up with a really long list, which is great. And I think all of those things are important and necessary. But sometimes the list gets so long that I can't really figure out how to navigate that long list. So sometimes I try to think about mobile robot navigation in 4 different buckets. There's perhaps a perception bucket that's trying to answer the question of what is around the robot in the environment. What types of things are in the environment? For example, is there a person in the environment, or is there a wall in the environment? And then maybe you might be interested in knowing whether those things in the environment are moving or how they're moving. And then there's a second piece, the second bucket, that I've called localization, which is really trying to address the question of where is the robot inside of that environment. And that question could mean a lot of different things. Maybe that means you're trying to just identify what road you're on. Or maybe it's important to know where exactly you are inside of a lane. So localization can mean a couple of different things. And then there's a third bucket that I kind of group things together that I'm calling task and route planning. And that's really concerned with how do I carry out some goal? What are the different steps I need in order to achieve a goal? So maybe I'm navigating a road network in order to go from my house to the bakery. What are the different roads that I need to take? Do I need to take a left on this road or take a right on that road? What are all the steps I need to reach my goal? Or sometimes task planning can be a higher level goal. So for example, maybe instead of how do I get to the bakery, how do I prepare for my son's birthday party? One step is going to the bakery and getting a cake. Another step might be going to the party store and getting some balloons. And kind of the fourth bucket that I kind of group things together in is motion planning and execution. So once I know what different steps I need, how do I actually plan and execute a safe route in order to reach those steps? So if I know I need to take a right on Massachusetts Avenue, my motion planner might be concerned with being able to steer the car and apply the brakes and apply the gas in order to navigate around the obstacles that I have in the way in order to reach that intermediate goal of turning right on Mass Ave. So today we're going to be focused on localization. Where is the robot in the environment? 2 really good references that talk a lot about localization are Sebastian Thrun's book, Probabilistic Robotics, and then also Sigwart's book, Autonomous Mobile Robots. They both have a lot of material that dives down deeply into the problem of localization, shows some of the math, especially in probabilistic robotics, talks a lot about the math. So it can be a little bit challenging to grasp, but I think it's well worth the read if it's a topic that's of interest to you. So we'll start out by what may be a review in Dead Reckoning. Have you talked about Dead Reckoning and an Ackermann motion model so far? Yeah. Okay, all right, good. So hopefully it will be a review. So on our race car, we can sense a couple of different things. And so we can sense the vehicle's velocity, right? So we have that velocity feedback from our motor controller that tells the robot how fast we're going. We actually measure that in electrical RPM, but we kind of convert it to some distance metric or velocity metric with a scale factor and gain. And then we can also measure, or rather we can assume from our command the Ackermann steering angle, so how far the wheels are turned left and right. And based on those 2 pieces of information, we can integrate over time the robot's position. Since we don't have a native position sensor on the robot, we don't know that we've moved 25 feet down the hallway and 5 feet to the left of the hallway. We don't have that sensor. Instead, we have to leverage the sensing that we do have on board, that velocity measurement and our assumed steering angle, in order to integrate our position as a function of time. So maybe you've seen a formula that looks a little bit like this, showing how your state vector propagates with your velocity as well as your steering angle. Is this formula familiar, or did you not get into that level of detail? Okay. Well, on race car, it's not too critical that you see or get into the details of this particular formula. The race car default nodes do this propagation for you. So there's I think it's called race car to ODOM, or VESC to ODOM, that takes the measurements from the electronic speed controller as well as the measurements of, or the commanded steering angle, and integrates the robot's position using this formula, where it calculates the x position of the robot, the y position of the robot, and the third element of our robot state vector, the yaw angle, the heading of the robot. So if you haven't derived this formula, it's relatively straightforward geometry to derive this formula. It's kind of an interesting exercise if you want to learn a little bit more. But one of the challenges with this approach of taking your sensor measurements from the robot and integrating it as a function of time is that you start to build up errors quickly, so that even though you kind of have an assumed starting position, eventually you will build up a large difference between your actual position and the position where the robot thinks that it is. And the reason is because all of your measurements have a small bit of error. Maybe they have a large bit of error, but we try to make our measurements have a small bit of error. And as we integrate those small errors over a long distance traveled, those small errors start to add up. So our robot starts to drift away from our anticipated position or our expected position from our actual position. So that can be a problem. That could cause us to drift off of the road, for example, if we were trying to stay within a lane boundary. Another problem with dead reckoning is that many times we task our robots in a map-centric viewpoint. So we don't necessarily tell our robot to go to coordinate x equals 30 meters and y equals 60 meters. Instead, we might want to task our robot in some viewpoint that is relevant to humans. So we might want to tell the robot to go to the cafeteria for us, for example. So it's often useful to think about how do we ground our robot's location inside of frame of reference that's relevant to humans, like a map or a street network if you're doing road-based navigation. All right, so that's a quick review of dead reckoning, some of the challenges of just relying on dead reckoning. Let's talk a little bit about localization. So one of the ways we can address those problems of dead reckoning is, well, maybe we can do a little better sensing, for example, decrease our errors. But we're eventually still going to drift away despite we can buy better sensors, and even though we have better sensors, we're still going to drift away to some degree. So one thing we can do is observe the environment and correct our integrated errors over time by observations of landmarks in the environment. So those landmarks can be any number of different things. We'll talk about a couple of them in this lecture. But we do want those landmarks to be easy to identify. So we want to be able to see a landmark and know that is clearly a landmark that we've seen before. It's unique to as great a degree as possible. So for example, the landmark in the lower left of the screen is a pretty useful landmark. We probably all know exactly where that landmark is. There's not too many other landmarks that look like that. Maybe there's one in Las Vegas. But for the most part, that is a unique landmark. We also want to be able to easily detect landmarks. So we don't want to choose landmarks that are hidden that we can't discover. And then where possible, we want those landmarks to be informative. We want to be able to see a landmark and get as much information about our relative position to that landmark as we can. That tends to be a tricky one, but there's a couple of good landmarks that can provide us with a high degree of location knowledge. You can have different types of landmarks. So we'll talk about fiducial landmarks in this class, where we actually augment our environment. We add fiducials or landmarks to our environment. But then we can also just use the environment itself as a landmark, so identify unique features in the environment that we use for localization. All right, so here's a graphical overview of what we're trying to do. So we have our robot. We started our robot at time 0, and we assumed the robot is starting at some initial position. Let's just say x and y are both equal to 0. And then the robot does some sort of movement, and so using that formula, our robot's motion model, we predict the new position of our robot. So maybe we predict it in the dashed arrow place there. And then we make an observation of the environment. So here we're making an observation to landmark that's number 1. It's a great landmark because it's easy to identify, it's unique, it's easy to detect. And so we make a measurement. We get some measurement back from our whatever sensor we're using to detect our landmark. And then we use that sensor measurement to correct the error inside of our dead reckoning. So the sensor measurement did not make any sense there, or the sensor measurement did not make sense if our robot was actually positioned in that dashed location. So we adjust the robot's location to where that sensor measurement actually makes sense. And then we can repeat that process again and again and again. So we predict our robot's motion using dead reckoning. So 10 milliseconds later, we repeat this process. The robot moved somewhat. We make additional observations of our environment landmarks, and then we update our robot's position based on our sensed data. And we continue that until the robot runs out of batteries or something else causes us to stop, like we reach our destination, hopefully. All right, so any initial questions about what we're trying to do with localization? Yes?
See with landmarks, then why do you even have to use dead reckoning? Why do you just rely on landmarks?
So why do you have to integrate? Yeah, so that's a good question. Maybe a couple different answers. Maybe there are places where you don't see a landmark. For example, in the case of using the Eiffel Tower as a landmark, sometimes you're going to be pointed in the other direction and you don't see the Eiffel Tower, or maybe the Eiffel Tower is obscured by trees. So that's one reason why you can't only rely on using landmarks. And the second question, I mean, it's a great question. And the second piece, I think, is that our observations, I didn't show it on that screen, but our observations, our measurements also have noise in them. So we might see the Eiffel Tower, but we don't know exactly its position relative to us. So maybe we know it's at a distance of 1 mile, or we think it's at a distance of 1 mile, but it's actually at 1.2 miles. So as we'll talk about later on, we can fuse our estimates of our robot's position with our estimates of our measurements in order to reduce the uncertainty of both. Good question, though. Yes?
Each landmark is different and unique. When you have to write a condition that handles each case separately.
I'm sorry.
If each landmark is different and unique, right? You detect each landmark. When you have to write a scenario for each landmark.
Write up so you do need to track each landmark, and so you do use every landmark position that you can observe. Generally, you try and use every landmark position that you can observe to update your location. So if you can see 2 landmarks, for example, you might want to try and use both of those landmarks to improve your position knowledge. Again, because your sensing of those landmarks might not be perfect. Did that address your question? Okay. Let's revisit it if I haven't answered it by the end of the talk. Yes.
So, don't cover this later, but what would you use your odometry or your dead reckoning for when you try and combine it with your landmark observations?
Yeah, so odometry is another acceptable word for dead reckoning. Those are kind of interchangeable. We'll talk about how we might combine them, but there is potential noise in both measurements, our measurements in our odometry as well as our measurement in our sensors, our observation noise. So we can attempt to combine our knowledge of both of those things to improve our estimate better than we can for each one individually. We'll talk a little bit about that in the last bullet in this outline. All right, so let's talk first about fiducial-based localization. So for some environments, we can add our own landmarks into the environment. We can engineer the environment with landmarks that are really convenient for localization. So we might place those landmarks inside of our environment, and we might measure the location of those landmarks. So now we have a good, what is called map of our landmarks in our environment. And because we've engineered our fiducials or our augmented landmarks in the environment, we can design them so that they meet the two properties that we desired in landmarks. So they're easy to detect as well as easily to uniquely identify. So for example, in our example here, we create these stars that are numbered so you can uniquely identify them. They're stars, so they easily stand out. So they're useful as landmarks. So there's many different types of fiducials that we can add to the environment. You can buy a lot of different fiducials off the shelf. You can kind of design your own. They vary quite a bit in what sensing modality that they use. So some of them might use optical sensing modality where you have a camera on the robot in order to sense something visually. Perhaps they use RF. For example, like an RFID tag might make a good fiducial in the environment. An RFID tag uses RF to provide a unique ID if you're close by. You might use things with like AR tags, which you may have started using a little bit yesterday. And AR tags are nice optical tags. And fiducials also will vary, or one of the ways you can classify different fiducials is the type of information that you can get from them. So some fiducials in the environment will only provide you with bearing information, so the angle to that particular fiducial. Others only provide range information, so how far you are away from that fiducial. And then others provide kind of a full state knowledge of where you are relative to that fiducial. Those tend to be nice to have because you just need to sense a single fiducial in order to get relative position. So let's first talk about bearing-only fiducials. So these are fiducials that only provide you with some idea of your relative angle to those fiducials. So one well-known example is the colored tags that are used in the robot soccer game. So they engineered this robot soccer field with these uniquely identifiable color tags. So there's like green on top of magenta or yellow on top of magenta. So the color combination is uniquely, makes it uniquely identifiable. And then you can use a camera to determine the bearing from your robot to each one of those fiducials. So it's a relatively simple computer vision task to threshold based on color, and then you use the position of the tag inside of the image to determine the bearing to that particular tag. So you can, in the bottom right, you can see that we can measure the bearing to landmark number 3 as some theta 3, and we can measure the bearing to landmark 2 as some theta 2. So that's good. Now we have bearing, but we still need to be able to convert that into some position in the environment for us to be able to use it. So it turns out that you can't just use a single bearing measurement because that doesn't tell you how far away you are from the fiducial. You can't just use 2 measurements of landmarks because now if you do, your robot can lie anywhere inside of an arc formed by those 2 landmarks. So in the example on the left here, those angles are the same for every single position of those robots there on that arc. You can't distinguish your position anywhere along that arc. So with bearing-only measurements, you need at least 3 fiducials in order to measure your position. So in the case on the right, we can uniquely determine our position by measuring the bearing to those 3 landmarks. So you need 3 position measurements, or 3 bearing-only measurements in order to determine your robot's position. So a really useful bearing-only localization system is motion capture. Has anybody seen a movie with special effects in it? All right, I don't know, I asked that. Everybody I'm sure has. So one way that they create special effects these days is that they have actors wearing these suits with little markers on them. And those actors go inside of what are called motion capture spaces. And the motion capture spaces have an array of cameras all along the ceiling and some other places. And all of those cameras look at those actors and those special reflective markers. And by using the bearing measurements from every single one of the cameras, they can determine the actor's 3-dimensional pose inside of that motion capture environment. Really neat systems for special effects, but the robotics community has also adopted motion capture. So we can put these tags on our robots and look at them with all of these cameras, and then we can compute the 3-dimensional position and orientation of the objects inside of our motion capture space with a very high degree of precision and accuracy. So there are a lot of YouTube videos that look a little bit like this in the bottom left of the screen, where you have flying quadrotors that are inside of a motion capture space, and that motion capture is actually providing the state information, the position information to each one of those different quadrotors. So here it's a little bit different in that the sensor is not necessarily on our robot. Instead, the sensor, the camera, are attached to the room, and our robot is actually the fiducial that we're measuring. So another type of fiducial are range-only fiducials. So these are fiducials that only provide you with range information. You know how far away the fiducial is, but you don't know in what direction it's coming from. One good example of range-only fiducials are beacons, underwater beacons for underwater vehicle navigation. So here you might have an underwater vehicle, a UUV, an unmanned underwater vehicle that's navigating in some underwater environment. And inside of that environment, you've placed some transponders. And transponders can be pretty simple. What they do is whenever they hear a particular ping, this is acoustic, so they kind of hear an acoustic ping, they will just respond back. They'll send out another ping. So if you're a UUV inside of that environment, you can send out your own ping, and then that ping will eventually reach those different transponders based on how fast the speed of sound is in water. Those transponders will respond, and then your UUV will eventually hear back those responses. And by timing how long it takes your UUV to hear back those responses, and by assuming a particular speed of sound in the water, you can determine the range, the distance to all of those different transponders in the environment. So that's good. Now we know distances, but that doesn't really tell us our position relative to those transponders. So instead, we need to have multiple range-only measurements in order to uniquely determine our position. So it's a little bit easier to see with range-only measurements. You kind of draw circles corresponding to the range of all of your measurements, and the intersection of the circles in the 2D case determine your position. So you need at least 3 circles to uniquely determine your position in the 2-dimensional case. In the 4-dimensional case, you need 3 or 4 spheres. It ends up being in the 3-dimensional case. So has anybody had a job where they've paid taxes? All right. Well, thank you. Micro pennies of your tax dollars have gone into building the most amazing fiducial-based localization system. So in GPS, the US government and others now have launched a bunch of satellites that provide you with orbiting fiducials, these really amazing devices that can tell you how far you are away from each one of these GPS satellites. So GPS doesn't work quite like the transponder systems of UUVs. Instead, each GPS satellite effectively broadcasts its time, and by leveraging the knowledge of several different GPS satellite times, you're able to determine the position to all of your GPS satellites. But it's an amazing system. The receivers that you need in order to receive these GPS signals are very inexpensive. A few dollars perhaps for a chip to a few $100s for a very sophisticated one. And the accuracy is really amazingly good on the scale of the entire globe. So you can generally know your knowledge within 5 meters or better. So why don't we use GPS for race car? I mean, it's like the perfect thing. I mean, it just tells us exactly where we are. The problem, well, there's a few problems. First of all, GPS signals don't reach indoors, so they wouldn't really help us. They also have limited, I mean, the accuracy is good, but they do have limited accuracy and precision, and 5 meters is not good enough for keeping a race car on its track. It's generally not good enough for keeping cars on their inside of a lane either. And then there's also this challenge of multipath, where sometimes even in very expensive GPS receivers, the GPS will update and you'll get some discontinuity in your position estimate, and it can kind of throw everything off and lead to some challenges unless you explicitly plan for that, which many self-driving cars do. So, and then the third class of fiducials are kind of the really nice ones. They give you both range as well as bearing, and some of them also give you orientation. So a good example of a range and bearing fiducial is augmented reality tags. So I think you had a chance to start experimenting with those yesterday. Is that correct? Okay, all right, good. So you know a little bit about augmented reality tags, but so they are able to look at these printed out tags, and they're able to determine the distance to the tag by looking at the scale of the image. The real tag has to have a particular size in order for that to work. So you can determine distance by looking at the scale of the apparent image of the tag in the camera image. You can determine bearing by looking at where the tag is inside of your camera image. And then you can also determine your orientation, at least reasonably well, by looking at how well that looking at how that camera image is skewed. So bearing and range fiducials are pretty nice, but they don't work in all environments. So for example, you couldn't really use augmented reality tags underwater, or at least not for very long distances underwater. So even though we've engineered these fiducials to be in our environment, we still can only sense them with some degree of noise, and that eventually leads to some errors. So for example, in the bottom right is an example of using underwater beacon distance, and you can see that even though there are a lot of valid ranges that your UUV would get, there are still some errors as well as some really bad outliers. So the sensors that we use are still error prone, so we have to account for that, even though we've engineered these nice fiducials. The other challenge with fiducial-based localization is that it requires you to augment your environment. So in some environments, you can't go out and do that. I can't go place an AR tag on every single tree in every single forest. That's just not practical. So instead, we can only augment the environment, or a subset of the environments that we might want to operate in. All right, so next we'll talk about one approach to addressing some of those limitations of fiducial localization, and that's actually using the environment itself as our set of landmarks. So now we're no longer going out and placing fiducials in the environment. We're instead looking at the environment and trying to identify whether there are any unique or interesting features that we can leverage for localization. So there's lots of examples of features that we might be able to use for localization. So for example, the corners in a building might be a good feature that we can leverage. There's lots of different corners in the building, so it's very hard to associate what corner are we looking at. But that's a reasonably easily identifiable feature in the natural environment that we can use. Other examples might be tree trunks inside of a forest environment. Those are fairly uniquely fairly easily identifiable features in the environment. So one question that you might ask yourself is, how would I go and represent that environment? And then second question is, once I have that representation of the environment, how do I associate my current observations with a particular position inside of that environment? So we're just going to very briefly cover this topic. We could easily spend several hours talking about different ways to represent the environment inside of maps. But a very popular way is to use what is called occupancy grids. So an occupancy grid is, you can kind of think of it like a picture of the environment, where each pixel in the environment or each cell in the environment has a particular value associated with your robot's understanding of whether that cell in the environment, that pixel in the environment is occupied by something, by some object, or free from being occupied in that environment. And it can be, it could be a binary thing, like I know there's that particular cell is occupied by something, some object in the environment. Or it could be more of a gradient where you have cells that may or may not be occupied by some object in the environment. And maybe you also mark, and typically you do, you also mark cells with your with being uncertain about whether there is any object in the environment or not. So here are a couple of pictures of occupancy grid maps. On the left is a architectural drawing of a particular environment. I believe that's a museum. And then the middle picture is what an occupancy grid might look like. So here, a pixel that is shown as white is believed to be free of obstacles. So that's somewhere where your robot can navigate. Obstacles that are shown, or cells, pixels that are shown as black are believed to have some object inside of them, so they are obstructed. And then shades of gray show some relative uncertainty about the environment. So the kind of middle gray, you're 50-50 uncertain about whether there's something in the environment or not. And then the version on the right uses the same convention. So white is free from obstacles, black are cells that are strongly believed to have obstacles in them, and then gray is uncertain. So when you have a map like that, one of the challenges is this problem of data association. So when my robot takes a measurement of the environment, if I have a laser scanner, I might get a set of points like this. How do I determine how that set of points match up into my environment in order to determine my robot's position? So that's called the data association problem. Does anyone want to take a guess where this particular laser scan is from in that environment? All right. Yes.
Oh, I don't even know how to describe this. Maybe it's like, see at the further to the top where the square empty space is, it's on like the bottom left corner.
Right here?
Down the hallway. Like right there-ish.
Yep, yeah, that's good. You're very good at data association. So now write a computer program to do that, and you're good. So that tends to be challenging for a robot. So here we were able to pretty quickly figure out where these laser scan points matched up. But it could be more difficult if you have a set of laser scan points that are from a hallway where you just have a kind of a linear set of points on both your left and right side. It's very hard to figure out where you are inside of the map along long hallways. And then the process of searching for this data association can be computationally expensive to try out all the different positions from these laser scan points. So using your environment to localize is a very powerful thing for many environments where we can't go and add a bunch of fiducials. But there are some of these challenges. Our real world might not be static. Our real world might be changing, for example, from when we collected or created our map. That's very frequently the case in many environments. So on a road, for example, you might create a map of the environment one day where you have a bunch of cars parked on the side of the road, and then maybe you come back on the weekend and all those cars have moved positions. So now your map has changed. Same thing can happen inside of buildings. Perhaps you've gone through and created a map of your environment with a bunch of doors that are shut, and then maybe the next day everybody wants to have open offices, so they open up their doors, and now all of a sudden your map doesn't match very well to your sensor observations. The real world tends to not be nice, well suitable for mapping. Not everything is in these nice wall shapes that you can easily sense with your laser scanner or whatever sensor that you're using to create your map. Can be cluttered with a bunch of extra things that move around. And then the whole question of how do you go and create your map of the environment is an interesting topic that we're not going to get into today. But that can be both time-consuming and challenging from an algorithmic point of view. And then there's this challenge of data association. So you can have things like perceptual aliasing. So you can have two sensor measurements that appear to be equally likely from multiple places inside of your map. You could have an environment where there's not a rich set of features that you can use in order to create a map. So if you had just an environment where you have a bunch of long straight hallways, it's very difficult to know which long straight hallway you're in from your current sensor measurements. And then also your measurements are still error prone. So you have noise in all of your different in all of your measurements. So trying to correct for those measurements can be challenging. All right, so now we'll talk about probabilistic localization. Yes?
I was a little confused though about the environment-based localization in the sense that if you already have, like if you take a picture of like your environment and you know like the map, it's like why not just program the robot to go like, say like I'm just gonna be like I'm gonna make it go down the hallway, then turn left and turn right, and then go like and just use sensors to make sure that the following goes path accurately. Like why can't I determine that path if I already know the map?
So that's the way you end up, that's the way most map-based localization algorithms do end up working. So you leverage a series of observations of the environment in order to better determine your position. You don't necessarily search from scratch every single sensor measurement that you take. So that is a common approach that you would use. You wouldn't take just some random sensor measurement with no knowledge. Most of the time, you wouldn't take just a single sensor measurement with no knowledge of your position and try to find where it fits.
So with like the world might change. Is it possible then to like just have it like you know the like for example we're in a building like you know the framework of the building you know that won't change in that sense. So then like you just like try to have the robot predict like moving objects and stuff.
Yeah, so I think that's a great idea. So there are certainly things in the environment that are more fixed and stationary than others. So walls tend to be stationary over long periods of time. Although you can't rely on that assumption being always true because people renovate their buildings. But it's an interesting research topic. How do you create a representation of your map that is robust to changes in your environment? That's an active research topic by professors here and graduate students at MIT, even thinking about how you create the right representations of the environment and how do you manage that map over a long lifetime, looking at what things are moving and what things are not. One of the reasons why it's hard is it adds additional state to your environment. So now, not only do you need to be considering whether each individual pixel is occupied or free, but you need to know whether it can be moved or cannot be moved. And How do you determine whether something is permanent or not permanent in your environment when you go and create a map? So good question. All right, so next we'll talk about probabilistic localization. So yeah, maybe before we jump into there, are there any questions about fiducial-based localization or environment-based localization? Yes.
For the fiducial-based localization, you said that you need to have 3 landmarks, or at least 3 landmarks in order to actually know the position of the robot?
So it depends on what type of information the landmark is giving you. So augmented reality tags give you both your range as well as the bearing, as well as your orientation relative to the tag. So for augmented reality tags, you just need to observe a single tag in order to uniquely determine your position relative to that tag. Bearing-based localization requires, in the 2-dimensional case, that you know at least the bearings to 3 tags in order to uniquely determine your position. And then for range-based localization, in the 2D case, you need to have at least 3 distance measurements in order to uniquely determine your location. So if you have 2 distance measurements, you can draw circles around those 2 distances, and that leaves you with 2 points, so you're not sure whether you're at which of those 2 points, so you need a 3rd circle to figure out exactly what that 3rd space is, what the 3rd picture is. And then so in the 3-dimensional case for range-only localization, you need to draw spears, and I'll leave that as an exercise to you to figure out how many spears you need to draw, because I think it's either 3 or 4, but I can't remember at the moment. Yeah, so with GPS, there's a lot of things you can do. There's a lot of tricks. You can leverage your motion and things like that. All right, so now we're going to talk about how we might be able to combine our estimates of our robot's position from odometry with our estimates of our sensing measurements in order to better and more robustly predict the position of our vehicle. So we already talked about the case where we are trying to figure out the robot's position in the environment, where we want to be able to update our robot's position based on our sensor observations. Here we're showing those sensor observations as being perfect so that we can uniquely determine our position of our robot. But in reality, those sensor observations might not be perfect. So we might get ranges that are slightly wrong, or in this case, drastically wrong. Or we might get bearing measurements that are slightly wrong, or for augmented reality tags, either our range or bearing could be slightly off. So we can't really rely on our sensors alone. So instead, we can try and leverage our understanding about how uncertain our measurements are in order to more robustly figure out our robot's current position. So let's say we've characterized the vehicle's odometry, and we know that in a single time step, our robot's odometry will be within some particular, in this case, we're showing an oval with a high degree of confidence. So let's say that we know that from position number 2 to position number 3, our robot is very likely inside of that particular oval. And then similarly, we can also say, by using our knowledge of the sensor measurement error, that if we observe these two landmarks, that we have some high degree of confidence that we're somewhere within that oval shown on the screen there. So the key idea here is how can we combine that understanding of our uncertainty in our position measurement from motion, as well as our position measurement from sensing, in order to better estimate the robot's actual position. So we can kind of fuse those two confidence ellipses into a smaller ellipse that has the same degree of confidence inside of it. So the question becomes is how do we actually do that? How do we maintain our robot's belief in its position as well as its confidence in its position. And that's a very detailed topic. We'll touch on it here, but again, for more detail into some of the mathematical basis, I'll encourage you to go to read some of the references that we gave earlier. It's a very interesting topic. So we can't say where the robot is exactly, but we can improve things if instead of saying where the robot is exactly, we can say where we believe the robot is within our state space with some degree of confidence. So we maintain what is called a beliefs function. So our belief function is some probability density function that describes our robot's position as a probability. So it's rather than saying our robot is at this particular spot with 100% confidence, we say instead our robot is somewhere inside of our state space, and in some areas of our state space we have higher confidence where the robot is, but it's not perfect confidence. So that function is called a belief function, so it's the belief over our state space x of t, our state space at time t, x of t. And then the part of the equation on the right is really just saying that our belief in our robot's current position is a factor of our robot's velocity as well as its previous position, the measurements that we make, as well as the map itself. So the formula is perhaps confusing, just kind of the obvious convention that our robot's understanding of its current position is a function of its previous position as well as the step that we made to our current position as well as our observations of the environment and our prior map. So we can use our belief space to kind of model our certainty of the robot's position. And it turns out that leveraging or explicitly modeling our uncertainty about the robot's position leads to a much more robust estimate of our robot's location. So one example inside of the probabilistic robotics book is copied here. And in this case, there is a robot going down a hallway. So it's a one-dimensional state vector, our distance along the hallway. And our robot has just a simple sensor on it. So it's a door sensor. So the door sensor will tell us whether we're in front of the door or whether we're not in front of the door. But our door sensor isn't perfect, so sometimes it will tell us we're in front of a door when we're not in front of a door, or sometimes it will tell us when we're not in front of a door when we are in front of a door. So there are some errors even though it's a binary sensor. So our initial belief state is uniform across our state space. So our robot has no knowledge about where its current position is. It could be anywhere along that state space. So the first step in localization is to observe the environment. So we're going to activate our door sensor. And in this case, the door sensor tells us that we are near a door. So we have what is called a measurement model that measures our confidence in our sensor. So if we are in front of a door, we believe the sensor to a degree, but we know it's not perfect. So that if we are in front of a door, we have a higher confidence or a higher probability that we are in fact in front of a door. So we can leverage our measurement model to update our belief state. In this case, it kind of just copies over. So now our robot believes that it is possibly or more likely in front or at one of those 3 peak locations there. But note that even though we have sensed the door, there's still some non-zero probability that our robot is not in front of the door because our door sensor could still be in error. So the next step is the robot moves down the hallway, and we have to update our belief to reduce our confidence because we have uncertainty in our motion model. So our robot might say it moved a meter down the hallway, but it could actually have moved 1.2 meters down the hallway. So our belief state loses some confidence in its estimated location. And then we repeat those steps over and over again. So then we activate our door sensor. We see we're in front of a door. We have the same measurement model. So the probability of observing a door that depends on our position and location within the map is shown there in red. So that we can kind of multiply our measurement model by our past belief, and that will have the effect of amplifying or increasing our confidence in the correct peak, and it decreases the confidence in some of the incorrect peaks. And then that process repeats. So we move down the hallway again. Since we've moved down the hallway, our confidence in our position decreases, and we can make additional measurements. So one of the challenges here is how do we actually represent that belief function? So here we're showing it kind of graphically, but a robot needs an algorithm to follow. One approach for representing the belief is by using Gaussian functions. So Gaussians kind of have some nice mathematical properties that lend them well to tracking a position over time. It's nice in that it has those nice mathematical properties and it's fairly compact. But the problem is it doesn't necessarily represent the true distribution of our robot. Particularly when it's a multimodal distribution. So when our robot believes it could be in any one of, in this case, 3 different positions, that single Gaussian function wouldn't well represent our robot's belief. So instead, another approach is to use a particle filter. So here we're not using an analytical function. We're instead going to represent our belief as a set of a large number of pose or position orientation hypotheses. Instead of kind of the smooth function, now instead we have a large number of different points in our space that could be possible locations of the robot. And we'll track those possible locations over time, as we'll see in a couple of slides here. So one of the nice things about the particle filter is that we can actually represent a multimodal belief space. So we are no longer limited to a single Gaussian. We can have effectively clumps of likely positions inside of our different set of hypotheses. So the idea is we're going to use this large collection of hypotheses, track them over time, reinforce the hypotheses that agree, that where there's a strong agreement between the sensor measurements and the assumed position of the particle, and weaken the ones that do not, and repeat this process over and over again in order to track our position over time. So the algorithm is, and we'll show this in a couple more slides here. Initially, we're going to seed our environment with a set of particles. We're going to make an observation of the environment. We're going to compare our observation of the real environment with our assumed position of the particles. The ones where there's a good agreement between our observations and our assumed position, we're going to weight them highly. And then we're going to do what is called resampling, where we reinforce the particles that have strong agreement with the observation and weaken some of the ones that don't. And then we're going to do a prediction step where we update the position of our particles based on our motion model. So here's a 1D example. So on the top part of the screen here, I'm showing the real world position of the robot. So in reality, our robot doesn't know where it is exactly. This is just kind of showing you the kind of perfect view of what's happening. So here we have a simple one-dimensional robot. So it's just working on a line relative to some wall that we've added in the environment. And our robot has a sensor that's a distance sensor, so it can determine the distance to that particular wall. And then on the bottom part of the slide, I'm going to show you kind of the algorithm view of what's going on. So we're going to do a simple example where we only have 2 particles. In reality, you typically will have many hundreds to thousands or tens of thousands of particles that you track. You can name your particles if you want. Don't get too attached to the particles because some of them are going to die. Spoiler alert. So here we have 2 particles. One is named spot and one is named dot. We've seeded our environment with our particles, so we just took initial guesses of where they might be in the environment. We just kind of threw them onto the environment, didn't really care where they went as long as we want them to be fairly evenly distributed in our environment. So we've now seeded the environment, in this case with only 2 particles. Normally, like I was saying, you would seed it with thousands. So the next step is we make an observation inside of the real environment. So we activate our distance sensor. So in this case, our distance sensor measured the distance from the robot to the wall. Our distance measurement wasn't quite right because it has a little bit of error or noise on it. And then inside of the algorithm, we try to calculate what each one of those particles would have determined for its distance to a particular wall. So the particle spot would have thought that its distance was, say, I don't know, 5 meters. And the particle dot would have determined that its distance should be about 3 meters. So then the next step was we compare our actual sensor measurements with the measurements that the hypothesized particles would see. So we can see that here there's a large error for the dot particle. So there's a big difference between the actual sensor observation and the dot particle's hypothesized sensor observation. And then there's a smaller difference in the error for the spot particle. So we weight the spot particle higher than we do the dot particle, so that we are saying that the position of the spot particle is more likely than the position of the dot particle. And then, yeah, this is the sad part. So the dot particle was not weighted very highly. So it effectively died out when we resampled our particles. So for all of our different particles, we select new ones based on the previous iteration's weighting. So the spot particle was weighted very highly. So maybe we can say, for this example, let's just say there was a 90% chance of resampling a particle in the spot particle's location. And maybe there was only a 10% chance of sampling a particle in the dot particle location. So it's much more likely that we will resample our particles in the spot location. Yes?
In order for this to work, like, wouldn't you already have to know your actual location of the robot, or to subtract, like, you can find the error, right?
Right. Yeah, so you need to know the actual, so you need to know the measurement, the thing that you got. So like I activated my distance measurement. Let's just pretend I'm the robot here, and the door is the wall. So I activate my distance measurement, and my distance measurement comes back as, I don't know, 12 meters. So now I have my distance measurement. And let's say that chair is one of my hypothesized particles. So in its hypothesized view, in its kind of simulated view, it can calculate that if that was the actual position, its distance to the door would have been 6 meters, for example. So now when I go to weight the particles, all I have to simply do is compare that distance measurement that I made in the actual world, 12 meters, to the distance measurement that my particle made in its simulated world, and I can see the difference is 6 meters. So I don't actually need to know where my true position is. I just need to know how well my sensor measurement in the real world agreed with my hypothesized measurement in my simulated world. Yes?
Sorry, I'm still a little confused, like, how you get these particles, because it's like, so you determine whether like a particle is good or not based on like the distance you measure. And so like, how do you then like, how are these like particles randomly generated and then like you just determine which particles are like closer to the actual thing?
That's right. So I started out by just randomly generating the position of these particles. So I have my bucket of particles, and I threw them on the ground, and wherever the ground they landed, they landed. I just randomly threw them out into my fake environment.
And then, like, you just reduce them based on like measurements you make as you move along.
That's right. So they start out completely random, and then the ones that happen to have fallen into the correct position or near the correct position of the robot's actual position are going to be reinforced because their hypothesized observations agree with the actual measurement. So they will be reinforced over time. And the others that were nowhere near the actual location of the robot will be weakened over time, and they'll die out, like poor old Dot. So here, for example, we had these two. The purple is the hypothesized distance that our particles thought that they would get in their simulated world. And then the red measurement is the measurement we actually took in the real world. So we can just compare those two. So in the case of Spot, there's a lot of agreement between those two measurements. In the case of Dot, there's a lot of error. So we weight them higher for the particles where there's good agreement. We weight them lower for the particles where there's not a lot of agreement.
So like just get like an area where who the robot is, like just like to calculate the error of our measure.
So to calculate the error, so it depends on what kind of sensor that you have. So for this simple example where we just have a distance sensor, we can kind of just subtract the two measurements. So we can imagine for each one of our particles, we imagine that we're that particle. So here let's imagine we're Spot. So in our imagination, Spot will say I'm, I don't know, 6 meters away from or 12.3 meters away from the door. And then we can imagine ourselves as Dot, and then Dot will imagine that it is 3 meters away from the door. Because we know the imagined position of Dot, we know the imagined position of Spot relative to those doors, to that wall. So we can just inside of a kind of simulation figure out how far away it thinks it is from the door. We compare that measurement to the actual measurement, look at how well there's agreement between the two. If there's good agreement, then we reinforce that particle by resampling, by choosing new particles in the same spot as the particles that were weighted highly. And we do that somewhat randomly so that maybe there's a small chance that we keep Dot, but likely we just reinforce the strong particles. All right, and then we repeat that process. So here, before we repeat the process, so now our robot moves, and so we have to update the position of all of our particles based on how far we think the robot has moved. So let's say the robot has moved 1 meter closer to the door. We update the hypothesized position of all of our particles, moving them 1 meter closer to the door, plus or minus some amount of noise. So that amount of noise depends on our motion model. So if we are very confident about that the robot, when it says it moved 1 meter, it actually moved 1 meter plus or minus a couple of centimeters, maybe there's not a lot of noise that we add to our position of our particles. But if we are highly uncertain about how far the robot has moved, maybe we add a lot of noise to our robot's position. So now we have robots, our particles in new positions, and the process repeats. So we take another measurement of the environment, our hypothesized particles, imagine how far they are away from the wall in the environment. Then we compare our actual measurement with our hypothesized measurement, weight them, resample them, update based on the next movement, on and on forever until you reach your goal or you run out of batteries or something. Yes?
I feel like an obvious answer, but wouldn't you just end up with your the measured distance then? Because you're just sampling different points that are coming up to the sensor measurements, right? Like the closest measurements.
Yeah. So yes. So if things are working well, you would eventually expect that a lot of your particles are there's a lot of agreement between where your particles are and what the actual measurements are. So that's where you're trying to get to. So initially, when you kind of just threw your particles on the ground and they landed where they landed, a lot of them won't agree. But because we're reinforcing the ones that have a good agreement between our actual measurement and our hypothesized measurement, we tend to build up a lot of particles in that location. And so that you're right, over time you hope to see a convergence of particles on the true position of the robot. So that's a 1D case. I thought I would briefly show you a 2-dimensional case. So this is a fairly well-known example. This is a museum environment, and in this case, each one of the red dots here is a particle. So now we have thousands of particles in the environment, but we still apply that same sequence of steps. So first we seed the environment with our particles. We just throw a whole bunch of particles in the environment. They land where they land. Then we make some observation with our robot's actual sensor, and each one of the particles hypothesizes a sensor measurement as if it was there. And then we compare all of those sensor measurements to each other. It's a little bit hard to see here, but there's maybe one particle that is, or a few particles where there's a good agreement between the sensor measurement as well as the hypothesized measurement. Then we resample as well as update the position of our robot. I think I skipped a step here for somehow. But then we repeat that process. We make an observation of the environment. We weight all the particles, so some of them there will be good agreement between our actual measurements and our hypothesized measurements. Then we resample to reinforce the particle locations where there's a lot of agreement. And then we make a prediction where the particles move forward according to our motion model. And then we can repeat that process over and over again. And so you can see that we have, in fact, converged into a kind of a good close grouping of particles where there's a lot of agreement between our measurement and our hypothesized measurements. So one thing that you might want to think about is what would happen if somebody picked up the robot, covered up its sensors, and moved it to another location at this point in time. For time, we'll skip that discussion. So I think you'll have, I think the labs will give you some general overview of the actual filter algorithm, so I'm not going to brief it on this page. If you read Sebastian Thrun's book, he writes the algorithm. It looks like this. For time, I'm not going to brief this particular slide. You might find that the implementations you find in the book might use a different numbering scheme for the different steps in the particle filter process, but it kind of just depends on where you jump into that repeating loop. But generally, you follow those steps that we just outlined. And here's another example that I'm going to skip because of time in order to get to a summary. So localization is a very important part of robot navigation. It tells your robot where it is in the environment. That's critical for being able to understand or to do those tasks of figuring out how do you get from A to B, as well as how do you navigate safely. We can use dead reckoning, but dead reckoning errors build up as a function of time. By observing landmarks in the environment, we can mitigate that increase in error due to dead reckoning. However, we still have to pay attention to noise in both our motion model as well as in our sensor estimates. If we explicitly model our confidence or our understanding of the sensor noise and the motion model noise, we can more robustly determine the position of our robot in that space. And one approach for modeling that uncertainty is by leveraging particle filters, which use a set of individual hypotheses or a large number of individual hypotheses and track those as a function of time, reinforcing the particles that have a strong agreement between our actual sensor measurements and our hypothesized sensor measurements. So we are over time, but I don't know what happens when we're over time, but I'm happy to try and take questions at this point. All right, Andrew's not chasing me out, so we probably have time for questions. Yes?
This is going back to Monte Carlo. So, the way that, so I noticed that like it was getting rid of, like it was kind of clustering of it, like different clusters. So the whole point then is like, based on the wall measurements it makes, it's okay, there's a wall 2 feet away from me, right? So then like, it knows it's somewhere along like one wall 2 feet away, and as it keeps going, it gets more and more exact. So my question then is, how long typically does it take for the robot to know where it is?
Yeah, so great observation. So you notice that there is clumping in multiple places. So there are multiple places in the environment where the robot might be based on our past observations as well as our current observation. The question you asked was, how long does it take to converge to a single grouping, a single hypothesis? And that's going to depend on a number of different things. It's going to depend on the type of sensor that you have. So for example, if you have, well, for the case of augmented reality tags, those generally can be uniquely determined. So you probably won't have a lot of multimodal distribution, so little blotches of pose hypotheses all in different places because you're able to uniquely determine your landmark. But if you have other landmarks where it's difficult to uniquely determine them, then it might take longer to converge to you might have to move longer in the environment in order to observe a series of interesting landmarks in order to uniquely determine your position. It can also, so it obviously then will depend on the environment itself. Do you have a lot of uniquely distinguishable features in the environment, or is there a lot of kind of aliasing, repeating features in the environment that are difficult to uniquely distinguish from each other? The answer is it depends.
Would it be beneficial then, like, if we're using like a parallel filtering system to like immediately just like move the robot around so like it can already start like determining where it is, because that's good the process, would it not?
Yeah, it is often an important thing to move through the environment in order to converge to a particular hypothesis. But again, it depends on what type of fiducials you're using. I think by using the augmented reality tags, you'll pretty quickly converge to a single solution because there's not a lot of plausible alternative hypotheses unless you model the likelihood of observing tag A and it actually being tag B. But they tend to be fairly robustly unique. So this is another example, speaking to your question about convergence to a single particle grouping. So this is another example from Sebastian Thrun, where they look at a robot with, in this case, I think there are sonar sensors inside of this environment. And in this case, because the environment has a lot of similar features in that there's a lot of similar doorways leading off from this main hallway, you'll see that there's actually plausible hypotheses that persist for a fairly long period of time until the robot actually drives into one of the rooms to uniquely distinguish it. So I'll just play this video here. So you can see there's a lot of clumpings here that are plausible because that's, each one of these looks about the same as any of the others. There's a lot of, the environment is symmetric. And it's not until the robot actually goes and enters the office until that other cloud is kind of extinguished. So again, you might not see the same behavior in your particle filter because you won't be as aliased in your sensing. All right, are there any other questions? All right, great. So we went very fast. You might have questions. I think you'll get a chance to explore particle filters on your own as part of the lab. And I'll be around for the rest of the day to answer any more questions if there any come up. All right, well, that's